Okay, time to find out if I just wasted 8 hours of my life. Hello, Internet. My name is Quinn, and this is Blondihacks. I've got a project coming up where I need to work on a piece of stock that's too large for my vise, so I need to be directly on the mill table, but I can't clamp it from above. I need to have access to the entire top surface. So I need to figure out a way to clamp it from the side. So let's go. When I was researching designs for this type of low-profile clamp, I came across Harold Hall's set of designs for these. That's an author who I'm sure you are familiar with. I've linked to his books before, and I can't show you pictures of his various designs because they are copyrighted, so I threw together some CAD models here of a couple of my favorites that I considered, so let's take a look at them. The first is this, which you've probably seen before. It's an eccentric, so I think it might be called a cam clamp, and it has an off-center bolt in the middle that you rotate, and it causes the outer diameter to shift against the part as you tighten it. And this has lateral clamping force but no downward force. This is a popular design, but I'm not crazy about it. I've never used one. Maybe it's fine, but I wanted to try something different. Second one I considered is this design from Harold. This one I like because it clamps horizontally and it also tilts a little bit and thus provides some downward force as well. Now the downside to this guy is it takes advantage of the depth of the T-slot. The T-nut, if you will, is integrated into it. And so you can only clamp in one direction, parallel to your T-slots. So that wasn't going to work for me either. Here's the design I came up with to hopefully solve this side clamping problem. So there's a large countersunk hole in the middle for a bolt that goes into a T-nut. So this whole piece clamps directly to the table, and then there's threaded holes in the back for set screws, and those set screws press on these plates at the front, and these plates form a flexure effectively that supply the clamping action to the part. They're basically just like little shields that protect the part from getting marred up by the end of the set screws. So the set screws are doing the clamping action, and then that big central bolt there is just holding the whole thing down to the table. I don't know for sure if this is going to work. Let's give it a try. I've got some 1018 mild steel bar here that I'm going to make these out of. It's pretty close to the right size already, which is very convenient. I want these clamps to be as low profile as possible, so they're going to be half an inch thick, which should give me a good clamping action while still leaving the top surface of the part clear. So I'm going to set this up here with a parallel in the vise and tappy tap tap that in, and we'll start by squaring up the stock. So bring the head down nice and close to the work, lock everything down, and we'll do a 20 thou pass on the top surface here just to get one surface flat and machined. And then we can pull that out, deburr it, clean everything up, and then we'll put that back in the vise with the machined face against the fixed jaw. Keeping everything nice and clean. Gonna put two parallels in now, and we'll use a piece of round bar on the unmachined surface to keep it from being influenced out of square by the movable jaw. And then I'll do another light pass on the wider surface here, and this surface is gonna need 2 passes from this cutter. All of my wider cutters are dull at the moment, so I'm making multiple passes. And then once again deburr, and now we have a machined right angle, so we put that right angle down into the back in the vise, once again up against the fixed jaw, and then we'll tap that guy in as well, again with the round bar on the unmachined face. And now I'm going to get some cutting oil in here because we're going to make some heavy passes. We have to bring this guy down to dimension. The short side facing down on the parallels is machined, so now we can get our dimension established on this axis. This is a 70 thou pass, and the cutter here is doing very well. Very happy with that. Got a couple of these heavy passes to do, so I'm actually using the rapids and going back to the other side and doing the cut in the same direction again, because cutting from this side, the hot chips are thrown away from me instead of towards me. And to that end, I've also got an acrylic chip shield here. It's magnetic, sticks to the back of the vise. Pretty cool. There's also some side wings that go on. I haven't attached yet, but that was donated to the channel by Pete over at MMNLS. I'll link to him in the description below. You can see that those chips are getting pretty hot there after a couple of passes. They're starting to turn blue, but they're mostly yellow. If we were pushing much harder than this, then we'd want to start thinking about flood coolant or something more substantial than just the a little bit of cutting oil brushed onto the part like we've been doing. And while we have the part set up like this, I'm also just going to square up the ends here with a little side milling action. Might as well. And since we conveniently have both ends exposed on the stock in the vise here, I'm going to run down to the other side and do it as well. All right, that's our stock squared up. It's looking pretty good. It's on dimension. I'm going to need to do some deburring over on the bench. And through the magic of YouTube, here it is all deburred. Looking pretty good. So now we can move on to adding features. I'm going to start by cutting this blank up into the parts. I'm going to make 4 of these clamps because that'll allow me to work with fairly large parts. So I'm going to mark these out on the stock using my calipers in a way that enrages many, many commenters. And I'm going to use the horizontal bandsaw to cut these guys apart. The saw cuts really straight, so I only have to leave about 100 thou for saw kerf in between each part. And that leaves me 20 or 30 thou to face off the end of each to clean up the saw cuts. Works really well. This is much, much more efficient than making 4 small blanks and squaring them all up individually. And this last part is just barely long enough for the vise on this machine. It's not held as firmly there as I would like, so I just put a C-clamp on the front there as well. The outfeed area on this machine is coplanar with the vise. Not all saws are like that, but in this case it is, so I can use a clamp like that, which is very handy. Now I need to square out those saw cuts and bring the parts to length. So I'm setting the first one up here in the vise, make sure the parallel's clear of the edge there, and I'm setting up an end stop so I can easily repeat this setup with the other 3 parts. And then I'm edge finding on the back corner there, which will be helpful later, but right now that allows me to establish the length of the part. So I touch off on the cutter, and you can see that I'm at 1793 there, and I want to be at 1750, which is 1.5 inches, the length of my part, plus 250, the radius of my cutter, which puts me at 1750. And so now I know I need to mill down to 1750, and if that's close enough to where I started, then I can do that in one pass. Otherwise I might have to do multiple passes. And since this setup is repeatable, when this is faced to length, I can just pull this part out, put the next one in without moving anything, and face the next one to the exact same length. So using an end stop and the DRO in combination like this means my parts will all end up exactly the same length without a single bit of measuring or any other fussing about. And after a little bit of deburring of those end cuts, we have 4 lovely little blanks that are all identical and are ready to have features added. Now I'm going to set them up in the center of the vise. It's always better to use the center of the vise when you can so the vise jaws don't get canted. You get a much more secure grip this way. And I'm edge finding again on the end, but not on the y-axis because we still have that reading on the DRO from before. We were relative to the fixed jaw there. And set up an end stop and then realized that I have the wrong parallels in there. I need to use the thin parallels, but luckily this setup is repeatable, so I don't have to edge find again or anything. I just change the parallels, put my part back in, and we're back in business. So now I'm going to a small 1/8 inch collet because I've got an 1/8 inch carbide end mill in here. We're going to make the round-ended slots that form the flexure on this part. I want to talk a little bit about those slots and why they're designed this way and why I'm going to make them the way that I'm doing. The slots might seem excessively wide because really all they're doing is providing a break in the material to create a flexible area, but I want there to be a curved radius at the end of that slot because this is a bending moment and it's going to tend to crack if there's any kind of sharp corners in there that can form stress risers. So I want that area curved, so that's why I'm using an end mill, and that's also why I'm not using something like a slitting saw, which would be a lot more efficient way to make this feature. Now, the other reason for the depth of the slot is that I need enough room to drill these holes in from the ends and have the 118-degree drill point come all the way through the solid part of the material. So it's kind of like a blind hole that needs a flat bottom, but I don't want to have to try and set up a boring bar or something to do that. So by making the slots just a little bit thicker, then I gain the ability to just use a simple drilling operation to get all the way down to the bottom, and also gives me enough of a radius to where I can make this with an end mill and end up with a nice flexure that's going to last a long time. The big downside to this approach, though, is that I can really only take about a 50 thou depth of cut with this tiny end mill, and the part is 1/2 inch thick, so that means I have to make 10 passes on each side to get all the way through this slot. It's a lot of passes that all have to stop in exactly the same place. So to try and mitigate that challenge, I thought I'd try using the end stops on my power feed. After setting this up, I ran it back and forth a few times with no cutter engaged, just to see how repeatable this end stop actually is. I can look at the DRO and see that the numbers end up in the same place on each pass, and the repeatability turns out to be lousy. So yeah, I've never used this feature before in the power feed, and I probably won't ever use it again because it just isn't precise enough to be of any value. The repeatability on it was something like 15 thou, and that's nowhere close to good enough for this feature. So I'm gonna have to do this by hand. So it's a total of 80 passes, 10 on each side of each part. After about 2 of those passes, the chip clearing ability of this little cutter quickly became overwhelmed. So I got the shot back out there to keep the slot clear while I'm cutting, and that also gets air moving over the cut to keep things cool. And so I got into kind of a rhythm here. You can see the little dance that I'm doing on each pass, and I didn't want to go any deeper than 50 thou on this little cutter and risk breaking it, so I just had to put on a podcast and put in the hours. After the first part came off the mill, I wanted to see if it would actually work. The milling went well, the features look good. So I put it up in the vise with an indicator and just measured the travel on those flexures. I'm getting about 5 thou there, which is pretty good. I wasn't sure if this area was going to be too thick. If it is, I can always just mill out an area in here to thin out the flexure areas, but so far it seems like it's going to work. So I went on and did the other 3 parts the same way. Next, I'll move on to the large central hole. So for that, I got to get the head on up and make room for the Jacob's chuck. I'm going to start by center drilling where that hole is going to go. And as I often do with this type of part, I'm doing each operation on each part and then changing tools and doing the second operation on each part. If you have a lot of parts to do, this saves you a lot of tool changing time. Next, I go down with the clearance size for the bolts that I'm using, which are 3/8 16. That matches my T-bolt hardware on this mill. And that should be a generous clearance fit, which it is. I want there to be some play there so that the clamp has a little bit of room to move on the table if it needs to. And now to counterbore these guys, I'm going to use a 4-flute 5/8 end mill. I don't have a proper counterbore for the type of cap screw that I'm using, and counterbores are really expensive. But this 5/8 end mill is the right size and it'll do the job. The depth of this counterbore is not super critical, so just a light touch with the quill and zeroing out the DRO will be fine there. And I'm feeding this guy down slowly with the fine feed on the quill. And I'm spinning about 850 RPM, same as I would for milling with a cutter this size. I'm feeding very slowly because this is not the type of operation that a 4-flute end mill loves to do. A 2-flute might have been a better choice here, but I didn't have one in the right size. But somewhere under that pile of chips is our feature, and yeah, that's looking really good. A little test fit there, and the cap screws go in there nice. They are flush, and the counterbore still allows enough room for that bolt to wiggle around in there if it needs to for alignment. So I did all 4 parts that way, and now we need to do some deburring for the next step. So I'm going to get out the Noga tools and other deburring items, which are all linked below in the show notes if you want any of these tools. I'm using various sizes of hole deburring tools to get to all the edges on the top and bottom of the counterbore and on the back side. Now for the slots, I got to bust out the needle files. So this is, where patience is a virtue. And I'm using a little round file there to get into the curved areas of those slots, make everything nice and clean. And now we can set up to drill the set screw holes in the bottoms of each part. So I'm once again setting that up in the vise, and I need to edge find on that x-axis again because I moved my end stop. And then I set up my end stop again so that I don't have to do this on each part. A little bit of cutting oil, and we'll spot these guys for drilling. Now, drilling these holes is going to be interesting because, as I said earlier, we have a very specific depth that we need to hit for these so that the drill breaks through at full diameter without impacting the flexure plate at the bottom. I don't want to leave a drill impression on that plate because that might interfere with the ability for the plate to slide however it might need to against the end of that set screw as it moves in and out. The perfect tool for that job is a depth stop on the quill, and this mill doesn't have one, but a low budget way around that problem is to use the end of your quill travel as a stop. So just move the head up or the knee down to set your drilling distance. Now I can't do that in this case because the head is all the way up and I don't have enough Z space to use the end of the quill in that way. So I need a real depth stop. Now I don't have one, or do I? Greg over at Priest Tools sent me this depth stop kit for the Precision Matthews line of benchtop mills. I've had it in a box for a really long time. I'm sorry, Greg, but I really needed one right at this moment. So I actually stopped what I was doing and installed his kit. This kit is really slick. It's got a spring-loaded half nut, so you can make rabbit adjustments up and down on the nut there. And there's no drilling or tapping involved in this installation. It installs in holes that were already there for some electrical wiring, which you can see I've got temporarily zip tied out of the way there. I'm going to do something better with that later. Now I wanted to see how repeatable this guy is, and you can see it's pretty good. It's within a couple of thousandths, and I think it would be a lot better if there was less flex in the stop here. You can see that it is moving a little bit. Now that stop has 2 other holes that could be used for mounting if you want to take the time to drill and tap into the head casting, so I likely will do that at some point just to make this a little bit more rigid. But I will say that I was able to install this entire kit in a few minutes, honestly, without even upsetting my setup, and I got back to business and was able to set my depth and drill my holes. Full disclosure, Greg sent me that kit for free, but with no strings attached, so I don't know, hashtag semi-sponsored. Now to set my depth, I've got a drill here that is slightly thicker than the thickness of the flexure, plus a little bit of extra breathing room, maybe 10 thou, and I just use that to set the depth of the drill and then adjust the depth stop to that point and drill away. And here's a photograph so you can see the bottom of that hole where there's not a single mark from the drill, so this worked out perfectly. We have full diameter all the way down and nothing more. A quill stop is also a really valuable part of a repeatable setup here, so I can easily do all 8 of my holes without adjusting a single thing on the mill or anywhere else. And now we tappy tap tap our holes for 3/8 16. I'm going in with a taper tap first and then coming back in with a bottoming tap and basically treating these as blind holes, even though technically they are through, but there isn't enough space at the bottom there by the flexure plates for a taper tap to get all the way to full depth threads. Incidentally, the tap drill size for 3/8 16 is Q on the Imperial letter drill scale, and I'm not saying that influenced my decision to go with this hardware, but I'm also not saying that. Back to the Noga bag of tricks for some deburring action, and then I'll clean off some excess oil there. And things are looking really good, and this was the point where I thought, you know, I should probably clearance the underside of those flexure plates just to make sure that they don't drag on the table and, you know, create some kind of interference or jamming there. So I set them back up in the mill and tappy tap tap them in, and then just aligned a 1/2 inch end mill such that I'm just shaving about a 10 thou depth of cut just along the front edge there. I don't want to go too far down the y-axis because I will lose support on the underside against the table. And just that little bit of a shoulder there should ensure there's no interference for the flexure to move against the table. Okay, finish time. I want to cold blue these guys, so we start by degreasing them, and we're going to use acetone for that. So I'm going to dunk them in there for a little while. Normally I would just wipe them down with acetone, but there's so many nooks and crannies on these parts, it's easier just to immerse them. And I'm using Jack's Metal Blackener here, which I've linked to in the notes below if you want to try this stuff yourself. So out of the acetone, they look very shiny and nice. And we'll let that air dry, make sure all the acetone has evaporated, and into the jacks they go. They turn pretty much instantly black, but let them sit in there for a minute to get all the nooks and crannies, and then rinse them off to stop the reaction, and then dry them thoroughly. And once that's done, we can come back in with some oil. Just about any oil will work. I'm using whey oil here, and the whey oil will seal the surface thoroughly. The cold bluing provides some corrosion protection, but the oil is an important part of that as well. So the oil will absorb mostly, and then you can just wipe off any excess with a paper towel, and the end result is some very nice looking parts. Okay, hardware time. So I've got my set screws here, and I'll talk a little bit about my selections here. I chose set screws and the cap screws such that they would both use the same size Allen key so that I can just keep one wrench in the box with these guys. For a part like this, I tend to design it around the hardware. So I chose the hardware that would fit in the space that I wanted to use and then kind of design the part around that. So let's give this guy a test run and see how it works. I'm going to clamp it on the table here, and you can see that using strap clamps as kind of a fixed jaw, if you will, is a key part of this because the side clamps don't really have any travel on them. So you need to be able to push the part up against that with some sort of sliding mechanism, and a traditional strap clamp is a great way to do that. You could also make something for that purpose. So I'm using a square to get the clamp roughly squared up against the table there, and then you want to tighten the clamps as evenly as you can to keep the clamp from rotating because it does just have the one central bolt. And then once it's snugged up against the part like that, then I can come back in and tighten up the clamps. So you only need a few thousandths of travel then on the clamps to clamp it in very, very tight. And then just like a vise, it's a good idea to tappy tap tap that in. This particular design does not have any downward force on it, as I mentioned earlier, so tapping it in is probably important. And this is about 1.5 inches wide, cut 50 thou deep, so pretty aggressive. It is aluminum, mind you, but you know, this is still a pretty decent test of the mechanism. I think if it wasn't clamping very well, it would probably move a little bit from this cutting force. And I'm so close to the end of my table that I ran out of travel here on the X, so I got to move the cutter off in the Y. But let's take a closer look at that cut and see how it did. And I will say that came out really, really nice. The finish on there is great. There is no sign of chatter, either visibly or audibly, and the part has not shifted at all. And I did make 4 of these, so I should be able to handle pretty large parts right against the table. And it's only 1/2 inch high, so I can handle pretty thin parts. Very pleased with how this turned out. If you want to make one of these, drawings for this and models are on my Patreon, and consider throwing me a few bucks there to get access to that, and also just because maybe you like my channel and maybe you want me to keep making videos. Thank you very much for watching, and we'll see you next time.